right. We have capacitors and dielectrics. Let's put down something. It's very important we put down something about capacitor. Now let's consider a conductor. Everybody knows from early classes. If you talk about a conductor, that is a property of a metal of a body that has the ability to conduct. To conduct. Now, when we talk about conductor, for quick example, about understanding concept, this is a conductor or a conducting body. We have discussed about distribution of charges under the principle of electrostatics. We said there is a property of, let's say this is carrying a charge of plus Q around. Charges are always distributed outside the sphere. You remember this? Please communicate. Outside the sphere. Now, and there is an opposite charge that is inside, because charges are always equal and opposite. Already discussed. Now, because this is a conductor, it's having a charge of plus Q. So we are checking the charge of plus Q. Then it is going to generate a potential difference we call V. Because we said if we are placing the material at infinity, then we are moving it from infinity to a point inside the what? Inside the conductor. So what we said in the other class was that the energy we take to move what? That particular PD from infinity to a point is called electric potential. You still remember that very well. So here what we are saying is potential difference V is generated. And because of this potential difference V, we are going to have what we call the dipole. Remember dipole? The control system of equal and opposite charge. So as a result of dipole that is setting along each of this charge, I'm only trying to explain concept. You have this, you have this, you have this, this, and this. So you have a dipole, negative, positive, negative, positive, negative, positive, negative, positive, like that, like that, like that. You can watch concept video on my channel. They are there. You have this, like this, like this. Now, this dipole is now the one that will set electric field around the conductor. So the electric field that is now generated around this are always in terms of the way we write electric field. This is the way you see it. These are the way you see electric field that is being set up. So when we talk about infinite conductor or infinite metal body, so what we say is that the amount of what? The amount of charge that is generated is proportional to the potential difference between the ends of the conductor. This is the characteristics of a metal body. Then from mathematics, you've learned from early classes, there will be a constant of proportionality. The constant of proportionality from this is now called C, and is called what? The capacitance of a capacitor. And this, a conductor can produce what? A capacitance. So the capacitance of a capacitor, we make sure your formula is now the what? The ratio of Q over what? Over V. That is the amount of charge per unit potential difference is called the capacitance of a capacitor. So the capacitance of a capacitor or a conductor or capacitance of a capacitor is given directly as C is equals to Q divided by V. So what I'm saying in essence is this, for you to understand very well, is that this is a famous formula you might have heard about in your early classes as E is CV. So it is just because metal has the ability to conduct, and because of the electric field is generated, bring about potential difference, and we've discussed about charge proportional to potential, and the constant of proportionality is C, we call its capacitor. So it's just like a bucket of water. That's the capacitor. Then the amount of water that bucket can hold, that is its capacitance. Are you getting that? So we can now write. Please write this and let's put down the notes. It's important. You can quickly write this so that we can put down the notes. Yeah, you can draw all this and we put down a note about important things. The first thing we want to talk about is about understanding the concept of a conductor and capacitor. So, and you've actually distributed how a metal body behaves like, but how a conductor produces potential difference about it. So please always keep this formula in mind because it is very, very important for us to watch. Please do that very quickly. Do that very quickly. We can take that in note. A note that is also important for us to understand this concept very well. That is, that we say the capacitance of a capacitor is measured in fards. the capacitance of a capacitor is measured in farad. Early classes, we discussed about this as well. That is, capacitors are measured in farad. And like I said under electrostatics in the previous class, that when you talk about electrostatic or body, we are talking about point charges, a very, very small amount of charges. That is why whenever you are doing measurements, always have it at the back of your mind that you measure capacitance in terms of you have microfarad, and remember 1 microfarad is equals to 10 raised to the negative 6 farad. Very important. Another one you can keep in mind, 1 nanofarad is equals to 10 raised to the negative 9 farad. And the last one you can keep in mind, 1 picofarad is the same thing as 10 to the negative 12 farad. This is the way we analyze. And measurement of all these your point charges can always need to be a small amount of either micro, nano, and pico. I hope you understand that. So when you see this, please don't run away because it's very, very easy to understand. So please, that is the introduction. And for you to write note, I believe you've done this in learning class. This is a level class, you know that. So we can't be talking about definition. But in case you have definition, for you to write, you can say capacitance, or people that like writing, is a property of an electric field. Capacitance is the property of an electric field in which two equal and opposite charges are separated by a distance to produce a potential difference between it. So you can see that these are stories, and stories is not physics, like I don't say. So somebody can just define capacitance as what? The amount of charge. Like I said, capacitance. We don't call this capacitor. Capacitor is the body itself. Like you can see the fan you have here, we have capacitors inside what? Inside the fan. But the relate activity is working. That's why I use the bucket and water. It's called the capacitance, and that is the definition. So it is the capacitance that is what? The measure of charge. Charge per unit what? PD. Charge per potential. The amount of charge that is what raising what? That is what? Raising what? One particular what? Potential difference. So please, there is not much to talk about it because these are what you might have met in every class. Q equals to CV. Always keep that in mind. When you base this on your formula, C is Q over V. What is the measurement of Q? Coulombs. The quantity of your charge is measured in what? Coulombs. We can always talk about that. And voltage is measured in what? In volts. So everybody should know that capacitance are measured in farad. You understand? So whenever you have two bodies that are separated by what? A distance. Such is the way you produce a capacitor. Every type of capacitor you have, early classes, you might have been told. We are still going to talk about classification of different capacitors now. But any type of capacitor you have, I get it now, it is always being produced by having two different conductors. A conducting body will now be separated by what? A distance. Then the distance of separation between them is the insulator. You know what they call insulator? So those insulator is now what we call dielectric material, which we call absolute knot. We've talked about that for those that we started. You remember absolute knot very well. Very good. So now, always keep it in mind that whenever you want to produce a capacitor, it's just for you to have two conductors separated by a distance. So that distance is the insulated body with the plate, and the insulated body are called dielectric materials. I hope I am communicating. So please always keep this in mind, and that is what we need to know about it. Now, we can also put another thing before we move to the next slide. We can also put another thing in mind, which is I think is very, very important, that we have different types of capacitors and we have different uses of capacitors. Early classes you might have been told that capacitor has a tendency to store charges. So you can just keep it in mind, or you can jot, you can put something down. Capacitors are used to what? For storing of charges. That's one. These are some uses of capacitor you can do what you can keep in mind. But basically you can just keep that in note as well and write that capacitors are produced by, just a note, capacitors are produced by placing two conductors by placing two conductors separated by an insulated body. The two conductors separated by an insulator is called what? Capacitor. That's how you make, and that insulated body we call dielectric. Dielectric. So what I'm saying, guys, is very simple. It's just having two metal, still coming to type of capacitor, I can see. Then I'm now separating them by, you can see, by a distance of d. So I'm placing an insulator in between them. Electric field is going to be generated. So that insulated body is now called dielectric material. Dielectric material. So which we denote by epsilon naught. So always keep that in mind. So dielectric materials are insulators. So because you can see direct questions in your tutor, like you'll be asked that which of the following can be used as a dielectric material. I can give you examples of dielectric material. We have a lot of examples. We can take that as a note here. Examples of dielectric material. You have what we call glass. Glass is an insulator. I hope students know that. You know that glass is an insulator. We have polyethylene bag. We have ebonite rod. These are examples of dielectric material. We have four. We can mention a lot, because we have discussed about electrostatics. All those materials that we rub. I mean, glass rub with stick, polyethylene rub with duster. I mean, now you still remember that now. A glass rub with stick will produce a positive charge. You remember that now? Ebonite rub with 4 will produce what? A negative charge. There is no charge produced when a glass is rubbed with 4 or ebonite is rubbed with 6. When you try to cross-link them, no charge will be produced. These are things you need to always keep in mind when you are talking about capacitor. So now by now, I hope you understand the difference between a capacitor and its capacitance. A capacitance is just what? The ability for what? The measurement of what? The amount of charge per unit of potential. Whereby capacitor is just the body itself. I guess that is what produced by what? A two conductor placed, you can see, plus Q and what? Minus Q, separated by what? A distance. Then you have what? A dielectric body, which is always insulated body. Please always keep that in mind. The examples of that are what you have, and that is that. So we move to the next part of it. I will talk about other types, the very quick one. So that's just the intro about that. And about uses, I said you have quite a large number of uses. You can always keep that in mind. You might have studied that in early classes. Capacitor can be used for rectification. Have you heard about rectification of current? Another thing is, apart from storing current, it can also be used for tuning of radios. These are some important use of capacitors you can always keep at the back of your mind. So for tuning of radio, for rectification of current means to change from AC to what? To DC. I hope you remember this, alternating current to what? To direct current. Please write, it is important to write in the class to understand this. This is A-level class, you have to write. It's important. Now we move to the next part. Now we want to talk about different types of capacitor and direct formulas you can always use to get what? Questions, especially for calculations on that capacitors. Now I told you for more concept videos, you can watch my channel. Now please, for those of you who are asking, now it's now Multi Academic Galaxy. That is where you can see, because I can see what is happening in this channel again. So now is now what has been moved to what moves Multi Academic Galaxy. To learn more about concept, derivation, and things like that, if you are listening. So on YouTube, you can always search for that and learn more. Now, about what I'm saying now, looking at the different types of capacitor, we are going to classify capacitor with respect to what we have talked about in terms of electrostatics. Remember, we talked about the first type of capacitor. Let's talk about single one. When we have a sphere capacitor now. Now, sphere capacitor can just be you have a circle like that, or radius of the circle is R, as you can see. We now know that Q is equals to CV, everybody knows that. So capacitance will be what? Q divided by V. So it is carrying a charge of plus Q, you can see, from what we discussed. And remember, I will not be showing quite too much of what proof and formulas, but you have to keep all these formulas in mind, because all these are going to be tested for during our numerical class. Like I've told you about that, all formulas I bring are very, very important to keep in mind. Now, about capacitance, remember, we have already discussed about it in terms of what? In terms of electric field. What is the formula for V? V is what? KQ over what? Over R. So if you go by that, you can do direct substitution. You see C equals to 4 pi epsilon naught R. Because R is the formula, and this is the formula for we use for capacitance of the what? Of a sphere or a spherical what? Conductor. Always keep this in mind because it's important. Direct solution, we are going to use this direct formula. 4 pi epsilon naught R. And if you want to derive that, you remember, for some of you are still looking, no time to derive it. V is equals to what? KQ by what? By R. Remember this? Now substitute V as KQ by R. Q gets cancelled out. We are going to have, and K is from 1 over 4 pi epsilon naught. Have it already discussed? So if you substitute this and substitute that, this is the formula you need to keep in mind. Because that is what you need to what? To have in mind. So capacitance of what? Of a sphere what? Of a circular a sphere or a single capacitor of a sphere is given by 4 pi epsilon naught. I hope you understand that. The next one, you can also talk about, but we have different classifications we are going to discuss. Now the last one we can also talk about is when you have more than what? More than one spherical capacitor that are placed at a distance to each other. There's also a way you can classify that. You just need to be careful when you are dealing with capacitors. Capacitors are simple. I get it, they are very, very simple. But you still need to be very, very careful. You need to be very, very careful because of our questions. Now, look at it, still on spherical capacitor, but look at this type of situation. Now, when we have more than one capacitor. Now, the first situation I'm going to analyze. I'm going to analyze very quickly the first situation where we have two different spherical capacitors that are separated. And we have distance from the center, and they are separated by a distance of L. The length here is L. Everybody knows there's the center. Electric field will be generated. We discussed this time and time again. So here we say this one we take as R1, and distance from here to here we take as R2. Now in this case we are saying L is very, very greater than what? The distance between the capacitors. Derivations and concepts are there on the channel, you can always watch. Now, for a direct formula, when you have two capacitors that are in what? That are spherical capacitors separated by a distance of L, the capacitance of that capacitor without delaying can be given directly by formula. You have 4 pi epsilon naught R1 R2 over R1 plus R2. Very, very important for students to keep in mind. So please always keep this in mind as you can be asked to solve the capacitance of two spherical capacitors that are at a distance of L or a distance of T from each other. So these are direct formulas. You just put in or plug in the values in numericals to get direct. So capacitance is 4 pi epsilon naught R1 R2 divided by R1 plus R2. Now, what about if that spherical capacitor are concentric? Students, you know what we call concentric? That is a circle inside circle. You understand that now very well. So now, if they are concentric, there's also a formula you can use directly because questions are not going to tell you what to use. But if you already know where the question is going, you don't have to waste your time. So for concentric, in case of concentric capacitors now, still on spherical capacitor, so spherical capacitors, we are still analyzing different cases of what? More than one capacitor. You can say the first one and the second one placed at a distance because there are some machines, you know, they use more than one capacitors. You know that very well. So now, if you look at the situation where I have a concentric now, concentric means circle in circle. From your mathematics class, you might have learned that. Now, if you have circles in circles, now what do you have, guys? We have, let's take an example. Please, you draw well. You have the first one, and we have the second one. Everybody know distance from here we take as R1, and the second one I'm taking from distance from here to here, I take as R2. So everybody knows we have this resistance plus Q. It's also what minus Q plus Q minus Q. Electric field will be generated. All those ones are concept every day. But for your own level, I told you what you need is just to know how to apply formula directly to get questions. Capacitance of a capacitor. Now we now have 4 pi absolute naught. We have 4 pi absolute naught R1 R2 over R2 minus R1. I hope you remember this. When you are asked to find the area to the area of the big circle minus area of the small circle. And that's how we have. You can see the difference between this. What's this? R1 plus R2. What's that one? R2 minus R1. So it's just to be very, very careful. Methodologies are simple when we start numerical calculations. We are going to see how we apply this to solve questions. So please, formula so far so good. Spherical capacitor, Q equals to CV is a formula. But when you have capacitors that are in form of circle, as we have already discussed, let me wake her up. She's sleeping on bed. Okay, welcome. Now, you can have when they are concentric or when they are placed at a distance of L or D from each other. So I hope you are getting this. And if you have questions so far so good, any questions? Any question from anybody? Can we move on? So fine. Now, the next thing now is also another type of capacitor we are going to keep in mind in your syllabus, cylindrical capacitors. As I've said, this is A-level class. Formulas are very, very important to keep in mind. Cylindrical capacitors. Now, for cylindrical type of capacitor, the capacitance of a cylindrical capacitor is also have a particular formula. So it's all about the formula. Derivation available at books, the academic galaxy. You can, but nobody asks you to derive. I have done derivation for those of you that actually like to prove. Because I love to prove to you, you know me very well. So now here, we can always have this, a cylindrical capacitor. Let's draw a cylinder. Please, students should draw very well. So we now have another big cylinder. So now you can see this. Now from what we have discussed, they are separated by a distance of d from each other. Each of them, please draw well. Draw well, this is important. So have a nice. They have a charge for separation. Charges are there. So this also plus Q. The first one we call A, the second one I call B. Electric field are generated. So the capacitance of this is given as I'm using the distance as d. I can see they are separated by the distance of that. They have different radius. You know that. They have 2 pi absolute naught L all over natural log of big radius. I call R2. Small radius I call R1. Natural log of R2 by R1. Now students should remember this, when my math students, you know what we call natural log. Hope you know natural log. Ln. This is LO. It is not in. It is what? Natural log of what? R2 by R1. Now hope you can press natural log with your calculator. For example case, you know how to press it and you see it. Ln. Ln. Very good. For example, look at this. If I give you a simple expression, math students, you guys are here. I'm giving you e raised by x and 1. My math student, we've done this in the math class. Hello, math student, please. What? If e to the power of x is equals to 5, the same thing. What's e to the power of x? The same thing of writing this one. Log what? I told you, whenever you write log of a number to the base of e is equals to 5. If you write it like this, it's wrong. So if you have a log of any number to the base of e, that is what you call natural log. So here, this is something as natural log of x. This format, everybody knows this is log x base e. Mathematics students, base students, you know this. Log x base e. But it's the same thing as natural log of x. So always have that at the back of your mind. So everybody know when you have square root of a number equals to this. Now if I ask you to solve this, I hope everybody can solve that. How will you get x? You square both sides. That is why, because we all know that squares are going to remove square root. Everybody knows. Now, the same thing is applicable to what? Exponential form. You can write mathematical equation in 2 forms. Logarithmic form and what? Exponential form. I am not taking math. This is not math class. But be that as it may, we can quickly explain to ourselves to understand it. So if I'm having this in an exponential form, I can rewrite this. We say e raised to power s equals to, I can rewrite this one in form of what? In form of a logarithmic form. Another we look at this, 2 raised to power 2 is equals to what? 4. So when you can write it as log, you have 2, you have answer is 4, then you have 2 equals to 2. Now this expression is indices form, exponent form. This expression is what? Logarithm form, because we say argument is equals to base raised to power of right hand side. That's the logic. I am not taking mathematics, so I don't want you to waste my time. I hope you still remember how to do all these things, like writing expression in indices form and exponent form. So you need to learn that. Whatever you have here, see, this is what, if you want to write it, it will be log, what is here guys? 5. I guess in the now, what's under E is equals to what? X. This expression here is in exponent form, is the same thing as this expression here in what? Logarithm form. So whenever log of a number is base of what? Base of E. E just means exponent. You can see it's IN. It is called natural log of 5. So please note that. In this natural log of 5 is equals to X. So always keep that at the back of your mind. So what I'm saying is that if you are given questions in cylindrical capacitor, and you are asked to find the capacitance, just keep it in mind that you have 2 pi epsilon naught of L divided by natural log of R2 divided by R1. You will press natural log of your calculator, LM. How do I solve this question? Square root is the opposite of what? Of square. What will be the what? How can I get S from this one? I will take natural log of both sides. Just as square root are for squares, natural log are for exponential. Do you understand? So if I say natural log of e raised by s, now only waiting the equal here. Now it will remain. So x will now be equals to what? Natural log of 5. Then I'll press on calculator. That is my answer. Do you understand? Just as square and square root are brothers. I get it now. E raised by x and what? Ln are also what? Just like they cancel out. Do you understand? That's the simplest way I can explain that to you. So please always keep that at the back of your mind, and that is that about that. These are simple questions, because in question is just to apply formulas. Do you understand what I'm saying now? So, but without question now, it will be difficult for you to actually comprehend all this stuff. The last type I'll talk about as type of capacitor, I think I should come to this side, is what we call line capacitor. Line capacitors. Now, about this type of capacitors, it is more or less like having 2 lines separated by a distance. You can see like this, plus Q minus Q, electric field will be setting. It's very, very simple. It's nothing like something, or maybe I should not talk about it and discuss it inside what we call a parallel plate capacitor. So let's go to the next part. Parallel. This is my spelling correct. Parallel plate, parallel capacitor. I hope the spelling of parallel is correct. Yes. Thank you very much. Parallel plate capacitor. Now, this is very, very important for students to keep in mind, because it is specially constructed in your syllabus for you. Parallel plate capacitor. Now, a parallel plate capacitor is just a type of capacitor in which you have 2 parallel plates. Let's take it like this for understanding's sake. Just like you can see, this is just a simple explanation. We do experiments on this in the laboratory. So everybody should listen to this, because we are going to do questions now on this one. Now, this is the simple form of capacitor you can see everywhere. You can see when I was explaining capacitor that I said 2 conductors separated by what? A distance. Now, it is very, very much like that. You have plus Q and minus Q at the charge. Here's what we have. The area of the capacitors are. So plus Q, you can just write plus all over this. I said I don't want to waste time, but we have a long way to go. And to the second one, you write what? The distribution of charges are negative. I hope students are following. They are separated by a distance of D. The distance of the plate is D. As you all have studied that, what electric field will be generated. So I'm representing my electric field like this. This is a simple explanation of the parallel plate capacitor. As you can see, students. So we have area of the plate and the separation of the plate. Separation of the plate is what? Is denoted by D, and the area of the plate is denoted by A. I hope students are following. This is a simple what type of capacitor that is needed to be known by all students. Because questions are definitely going to come out of the question, whether you like it. Now here, the simple way for us to get this, we have already discussed that what capacitance is equals to what? Q over what? Over V. Remember this? Q is equals to what? CV. Now listen guys, Q equals to CV. Now, as you can see, electric field is generated because there is what? A potential difference within what? Within the plate. As we all know very well from our early classes that we studied under electrostatics, please listen. Can I move on? Yes. Now we know that what I want to be showing you, but I don't want to be deriving formula again. E equals to V by D. I don't like deriving formula, but let me just show you this one. It's wastes a lot of time because I have a lot of examples I will still solve. I hope you are following. Now from here, let's make this your formula. What is V class? V equals to what? ED. Yeah, directly I said go and watch Jose Academy Galaxy to learn concept. LO is there. You understand? But it's not needed. It is when I start example now, we now see if you can use this formula to get the right question. I am very sure some of you, conversion will still be the problem. Millimeter to centimeter, centimeter to, that is where some of you make mistakes. So that's why we need more practice questions, so that you don't fall that victim of mistakes when you are doing your homework. Because I will not be there. Now here, from here, everybody knows this is electric field. I mean, electric field that is generated within the plate of the capacitors. Now, if I go by this, directly I can say V is equals to, you remember this? Guys, you remember this is absolute naught over permittivity. I mean, you have this sign over permittivity times T. Now remember, you told me in the last class that you don't know how to write this. What do I call this one? Charge density. Remember that very well. Now, I told you charge density is equals to what? Absolute naught times what? Times electric field. Don't forget this formula. Because you are talking about capacitors and dielectric. Can I move on? Do you remember this? Charge density. Now, what is the definition of charge density? We said it is the ratio of what? Quantity of charge over what? Over the area. Now, I will now move on to the next part. I will say V will now be equals to, now charge density is what? Q by A. I'll now have Q, I'm not going to show this, but let me just show, over A, absolute naught T. Any problem with this? Any problem with that? No. Then we now come back here, substitute this here. You now say capacitance of a parallel Q here is Q. I'm using small Q. For understanding say Q gets cancelled out. You now have E naught A by D. This is the formula for capacitance of a parallel plate capacitor, which students need to keep in mind every time you are facing questions. Direct formula, direct methodology you are going to use to get answer. Capacitance of a parallel plate capacitor is absolute naught A over D. What does A stand for? Area of the plate. What does this stand for? Distance between plates. What does absolute naught stand for? Permittivity or dielectric. Now always have that. And remember, we have discussed this. Relative permittivity or dielectric is what? The one in medium divided by the one in mercury. So students need to know this because it is important. So this is the formula you need to keep in mind. Absolute naught A by D. Absolute naught is called dielectric because we are talking about, like if you call it permittivity, it is not a problem. You understand? But this time around, please help me with more and sleeping. You can take a job. Don't sleep in class. Now this is it, and this is what we need, guys. And this is how we are going to solve questions on this one. But you can be asked in theoretical form. Yeah, fine. That list 3 factors that affect the capacitance of a parallel plate capacitor. I have told students of physics, once you know formula, you can answer any theoretical question. What are the 5 factors that affect capacitance? Area of the plate, distance of separation, dielectric material. They can also ask you questions directly like, what are the effects of, now, when the distance between the plates of a parallel plate capacitor is increased, what is the effect on the capacitance? The capacitance will what? Reduce. Can you see that here? From here, science student talk. What's the difference between capacitance and distance? Capacitance is inverse proportional to what? Distance. It means the higher the capacitance, the lower the distance. What's the difference between capacitance and area? Capacitance is direct proportional to. So if the area of the plate is increased, kilo must share the capacitance. Capacitance will also do what? Increase. Do you understand that? Because you see these questions time and time again in your what? During your exams and mocks. So don't make this. And the last one, what's the difference between capacitance and dielectric? The higher the dielectric material, the higher the what? Capacitance. Some of your textbooks will tell you that dielectric material has no effect on capacitance. Now lie. I'm standing here to tell you that is a big lie. So please always don't follow what all your other textbooks, and please use good textbook. So the effect of the electric material is that what it increases the capacitance of the what of the capacitor. So if you remove the electric materials there, the capacitance of the capacitor will also reduce. So the only thing that if you reduce, will increase the capacitance is what? Is the distance of separation. So that means the higher the distance, the lower the what? The capacitance. When they are closely packed, what will happen? The capacitance will be what? We take an example here for understanding it. So I told you too much of theoretical concept. Let's take one example. Right? This, we take an example. Waiting. We take the first example of today before we move to the next one. I hope you are ready. The first example, let's just solve this one very quickly. A parallel plate capacitor. You are writing an example. Let's just take one first. Then we move on. We see how that concept. I have divided this class into two sections of capacitor. You still have after capacitor and electric. The next topic is electricity. So please take it gradually. Each time we finish the resistance of electromagnetism. Now we are saying something. I said a parallel plate capacitor separated by a distance of 10 centimeters. A parallel plate capacitor separated by a distance of 10 centimeters. A parallel plate capacitor separated by a distance of 10 centimeters. Is having an area of separation of 0.2 meters square. Is having an area of separation of 0.2 meters square when positive charge pass through it. When positive charge is passed through it. When positive charge is passed through it. Full stop. Calculate its capacitance. Calculate its capacitance. If, open bracket, if epsilon naught is equals to 9.0 times 10 raised by negative 12 farad per meter. If epsilon naught is equals to 9.0 times 10 raised by negative 12 farad per meter, F/m, or Fm raised by negative 1. This is a direct question I believe everybody has. So I wait for your solution, please. If you are free, let me know. Calculators is allowed. You can quickly solve it. So what will we answer to that question? Please be mindful of conversion, because conversion is one of the most important things you can always keep in mind. Now we are looking for capacitance. Most questions may not ask you to look for capacitance and ask you to look for area or anything. You understand what I'm saying now? It's just to substitute directly and get the answer. So from here, everybody knows capacitance of a parallel plate capacitor. Please, you keep quiet. I'm not supposed to tell you that. Capacitance of a parallel plate capacitor is absolute naught A by D. Already discussed. In the question, epsilon naught was given to be 9 times 10 raised power negative 12 times area of the plate. Please, class, what's the area of the plate? Communicate, please. Area of the plate 0.2 meters square. 0.2 meters square divided by what's distance of separation? What do you call that? So I have to convert 10 centimeters to meter. I also know that is 0.1, Abi. 0.1 meter. 10 divided by 100. Do you know that? Is 0.1. So everybody can solve this and you put your answers of capacitance in farad. Very important. You can see that this we cancel. This is just as 2. This is 18. 1.8 times 10 by 11. Are you okay with that? Or you are still pressing your calculator? How many times did I tell you on how to divide? It's simple to divide. See, this is 2 times 10 to the negative 1. This is 1 times 10 to the negative 1. What do you know? Yeah, that's the answer. I just want to show you. You don't need calculator almost now. This is minus 1 plus 1 is 0. Get cancelled. This is 2. 9 times 2, 18. So if I say 1.8 times 10 to the negative 11 farad, question answer. So I don't need to waste my time. This divided by this is 2. Always keep it at the back of your mind. Whenever you have this divided by this, it's going to give you 2. Because it's 0.1 times 2, that is 0.2. Everybody should know that. So please, you understand what I'm saying? Always keep it at the back of your mind. So that's the answer to that. I hope you understand this concept. So always keep it at the back of your mind. The electric material will increase the capacitance of a capacitor. Can we move on, or you are still writing? Slow writers. I'm waiting for you. If you have a question, you can ask me. I'm here. If you have a question, you can ask me. No questions. Proceed. Any problem? Are you sure? All right. So let's move on. Please write fast. The next thing is what we call the work done. The next concept, work done in a parallel plate capacitor. Work done in parallel plate capacitor. So students should be careful when we talk about work done in parallel plate capacitor. As we already discussed about work, we talk about the total work done in terms of energy. Work is always done in terms of the form of energy, blah, 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 blah. Now, let's quickly analyze this and understand it very well. Now, the work done, I told you about potential energy in the last class. That's the work done in assembling what? Charges, Abi? From infinity to a particular point. Very good. Now, here, hope I'm not too fast. If I'm too fast, let me just reduce the pace. I am kind of too fast, I'll be okay. Don't worry, I will reduce the pace. We have a lot to cover, that's why. And you know about me, I always want to cover everything in syllabus. It's important to know everything. So that you will bless me. When you see question and you know the answer, you know the formula, you are going to say blessings to me in your mind. Then when I pick my book, it's sure for me. It will be there. Do you understand? So that's one thing. So let's move on. Now, work done in a parallel plate capacitor. We talk about parallel plates. I'm taking them like that. I connect it to I have 2 parallel plate capacitor, X and Y. Parallel plates. It can be in that form. You know the other one I do was horizontal. This one I'm placing them what? Vertical. What does it mean? Because I want to connect the end to a battery. I connect this one to positive side and this one to negative side. So you can see I'm connecting this to the negative side of the battery and I have a switch. If the switch is closed down, what I'm saying is that potential difference, please listen, will flow. Please listen. Potential difference will flow. We have plus and minus. Plus is always longer than minus because some of you have not been to the laboratory before. So let me help you. So now from here, remember we said this is a parallel plate capacitor. They have charge of plus Q and what? And minus Q. Electric field will be generated between the plates. Already discussed all those shorty things. Now this is a key. The key or the switch is closed down so that negative charge will move like this. And always note, charges will go in that place, plus and minus. Charges always move from what? Potential move from negative to positive, clockwise manner. Everybody know clockwise now, the hand of the clock. Now, without wasting time, what we are saying here is that because potential will be evenly distributed, plus and minus, they cancel out. We know the formula we always use is Q equals to what? CV. Abi? Is that not the formula we talk about? Very well. Now, good. Now, from early classes, we are talking about work done in a parallel plate. Now, work is done. We say work is equals to quantity of charge times what? Potential difference. Already discussed in the last class. Now, from here, what do we call Q? SR. What's Q? CV. So, work done will now be equals to CV squared. Students should keep this in mind because it is important to solve questions in form of Please, do you understand that now? So work done inside the parallel plate capacitor is what? CV squared. Whereby C stands for capacitance. V stands for what? Voltage. Or potential difference. I hope we are communicating very good. So always have that. And work is always done in form of what? Energy. What's the SI unit of work? Joules. Work has SI unit of joules. I don't need to do direct calculation here. Everybody can get that because I ask to calculate work done. Sometimes I can ask you to calculate the capacitance when I'm giving the work and the potential. So just substitute the relationship. That is that about that. Now the next thing is energy inside what? A parallel plate capacitor. Now let's continue in sequence. We move from the first formula we have discussed. So far you say, guys, I'm too fast. I'm trying to take it slowly. And please ask questions if you have any doubt. You are always free to ask questions. You are always free to ask questions if you have any doubt. Yeah, your question. Well, the Q is CV. So C, V, V, plus VV. VV will be squared. You understand? So just, you know this formula. I know you guys know this formula. But this is how it was. It was coined. It's just like that. And I say everything is simple if you know it. It's simple. Everything is always simple when you know it. It is when you don't know something that you will talk. So can I move on to energy? Now, energy. Now we are talking about a parallel plate capacitor. And because it is parallel plate capacitor, you have to understand something. Now, the total energy is done in form of work. So I can say energy in a parallel plate capacitor, energy. Anyway, we can actually derive it. It's very, very simple to derive. But because I've told you, I don't want to waste your time. So, but normally, it is a parallel plate capacitor. We say R multiplied by absolute naught times E multiplied by A multiplied by D. I don't have time to be deriving anything. Don't worry. Final formula is what you need. So from here, you say energy in the parallel plate capacitor. I hope you guys can see this. Help me check. Can you see from here what I'm writing? Yes, thank you very much. Now, energy will now be equals to, from there, everybody knows what electric field stands for. How do we write electric field? Now you know the formula. Electric field is always equals to, where I talk now, E equals to what? And you remember now, I don't give you this formula before. Absolute not equals to E and electric field. This one is electric field. So electric field is always what? Charge density over what? Absolute not. Abi? This is the way I want you to be writing electric field. It's very, very important. Do you understand that now? So if you go by that, and you know this one is Q over A, always keep this formula in mind. That is why we are taking capacitors and dielectric. The dielectric is very important in everything we are doing because it increases the capacitance of what? Capacitor or capacitors, as the case may be. Please don't sleep on by. Now here we have, remember this is Q by A. I want you always keep this in mind. The formula is very important because you are going to use it to solve a lot of numericals. Lots of numericals. This is Q by A. Remember that one? Now if it is Q by A, what will be the formula now? Q over A absolute naught. So this is the formula you need to keep in mind in terms of dielectric. Whenever you are talking about electric field that is affected by what? Dielectric. So if I go by that, everybody knows this will turn to something like this. I don't have time to this deriving formula. Now remember this, guys. E naught A over D. E naught CO. Q is now another way. You say E is equals to, I like physics so much. But this is about formula. I just want to show you. Final formula is not unique. What is Q? What we say Q over A, like this is Q over A. What you E naught A by D. E naught A by D is what? Is capacitor. So I can say energy is now R C remain 1 V squared. This is where you are going. So energy in a parallel plate capacitor, you can see, you all know this formula. Why it was being coined, nobody knows. But now I've shown you. So always have that back of your mind. Work done in what? Parallel plate capacitor is CV squared, whereby energy is what? Half CV squared. It's as simple as that. You said? Electric field is what I've done to this now. I've done electric field to QE not E. Electric field is QE not by A. So always keep that in mind. So and I know that E not A by D is C. So everything gets cancelled out. I only have what? I only have 1 V that is remaining there. You understand? But all things being equal, nobody will give you question in terms of V, in terms of what energy density. It is always in terms of your what? Half CV squared. And that's why I said your physics is so simple. Your own physics you are doing at this level is so simple. It's just for you to know basic formulas and interpretations of it. I hope we are communicating. Your question? Ask. Ask your questions. I'm waiting. Yeah. Yeah. A times C. I have only taken C now. C. E naught A by D. What I've taken is E naught A by D. Remember, I have Q by A here. You know, this is always, what do I call this sign? Charge density. A over D out. Q over A. So what happens to this now? You can see that A is here. A gets cancelled out. Is that not so? A gets cancelled out. Now another thing you can also watch is that I have absolute naught also gets cancelled out. Because absolute naught is under here. Absolute naught is under here. Okay, so Abby, can you see that? And remember something again. I told you that Q is equal to what? CV. That is where the last one is from. Q here, I will turn it to CV. So what is V times V? That is where what V squared is coming from. But all the same, listen, derivation, like I said, is not that important as understanding the methodology. You understand that? So understanding the formula is work done in what? In a capacitor is what? CV squared. Energy done, the amount of energy in the what? Parallel plate capacitor, any capacitor what? Half CV squared. Now, but there is a man, they call what? Joule's eating effect. Have you heard about joules before? Joules. Energies and work are measured in joules. I hope I'm communicating. Now, according to joules, joules actually told us that as what we call what? Heat dissipation. Chika, come to the front. Now, there is what we call heat dissipation, heat loss. That is, in every property of what? Of a metal, a material. We can explain this. Concept video are available. I've said that time and time again. Now, there are sometimes your phone, you touch it. We are still going to talk about all these things. What we call charge density. Apart from charge density, what we call J, current density. Have you heard about current density before? Sometimes you see your phone now that we are making recording now. If the phone is what, so weak, or there are some electrons that are escaping between. You can see when I started the class, I draw a conductor, and I tell you about what you have. Some electrons are inside. The charge, the positive charge, they are located outside. So if you come to a time when there is what loophole, some electrons start escaping from that inside and they are coming outside. At this point when electrons are coming outside, that is when you start seeing what? Formation of heat. I know you guys know what I'm talking about. Your phone starts what? Heating up. We say heating effect of current. Because some electrons that are supposed to be occupied at a particular point are now escaping. Sometimes when the battery is very, very bad, electron that is composed, that is compressed inside the battery are now moving outside. So when you charge, you say, if I charge by 50%, my phone will just move to 100. When my phone is at 30%, it will switch off. What do? You change your battery, something like that. Some of them are the component. So what I'm trying to say is that there's only what we call heating effect of current. Heat are always escaping, whether you like it or not. And there's a special form of heat, we said heat loss by dissipation. What's the meaning of dissipation? Grammar student. Dissipating. That is coming out. Something dissipating. So the amount of heat as a result of what? The material being heated. Heat to ejade because of what? Because of heat. The heat that are coming out. I guess that's what we call dissipation of heat. Now, the dissipation of heat dissipation, which is the last one I talk about under here. Heat dissipation. I want to talk about heat dissipation. Dissipation. Heat dissipation is just the total amount of what? The total amount of work done inside the what? The capacitor. What's the amount of work done? CV squared. It's just, let me just say that. Work done in capacitor minus the energy of the capacitor. Because I said the whole thing is what is composed inside the capacitor. But some of the electrons are now what? Escaping. So if you want to get the amount, direct formula we say, what's this one? CV squared minus half CV squared. What's 1 minus half? Half CV squared. So when you see question on the amount of heat lost by a capacitor, heat loss in form of dissipation, it's always also the same thing as what? Half CV squared. I hope students are getting this because all these formulas in ring form are going to be used directly to solve questions. Directly. So you don't tell me when we start solving questions now that something has not been done. So heat loss is the same thing as heat dissipation because of grammar. I calculate the heat loss inside the capacitor of capacitance 5 microfarad and what? Potential of 10 volts. What will happen? That is half times 5 times 10 raised to minus 6. I hope you understand where minus 6 is coming from. Then times what? Times 10 volts squared. Have it? That is the answer. Very simple task. Are you not enjoying this? It's simple now. Is it hard? It's very simple. It is what you don't see that is hard. You have a question. You heard this country. Now let me get water for her. I heard this country. She needs water. So the next point, guys. Let's move on. Are you true? Kika, where are you coming from? From your house. You cannot talk. From your house. Ah. She's not in school. She's not around. She travel. She travel for Valentine. That's good. It's part of life. I hate going on this side. Next point. Next point. The next point, the next checklist point is forces between plates of capacitor. Forces between plates of capacitor. Forces between plates of capacitors. That's the next one. Hope we are moving. How many minutes are we? Very good. Almost an hour. Okay, because we have a 2 hours class. So I just want to do a lot of calculation. Yeah. Forces between, this is what we have given us. This is what we have us to do. You just say that. So we have to limit it to an hour. Now, forces between plates of capacitor. So we need to understand this too. It's very, very important. Please don't make noise. Let's come to it. Now, a quick one. Forces between plates of capacitor. Let's quickly analyze. If you are ready, I'm ready. Can we start? Now, from what we've studied, we said Q is equals to CV, or basically you can say C is equals to Q divided by V. Everybody knows that now, and I'm happy for that. Now, if we have two parallel plate capacitors like this, every time we drop, separated, connected to a battery, the P is closed down, and we have something like this. Positive charge and negative charge, like one we have talked about. Electric field will be generated. Now, so far electric field is generated inside the plate. We say electric field generated from what we have studied before. We say electric field is the same thing as volts per unit what? Distance. I hope students to remember this. E equals to V over D, or you say V equals to ED, anyhow you want to take it. It's still the same thing. Now, what I want to bring out here, guys, you need to understand and listen carefully. Now, there are two components of the parallel plate. We have the first plate we can call plate X and the plate Y. Each of them is moving. You can just pick a point, just like this, inside the plate we call EX. Now, we have two charges, plus Q and what? And minus Q, that are acting on it. So if we want to calculate the electric field that is flowing inside this parallel plate, from what we have studied, we say EX or E positive is the same thing as E negative. So the amount of what at a point inside the what? Inside the field there, we call EX, it will be the same as saying EX divided by 2. Where is the 2 coming from? I have two different what charges. I have charge of plus Q generating a field. I have charge of minus Q generating a field. So what I'm trying to say now is that the amount of charge at any point inside this what? You understand what I'm saying now? Because there are two different what? Two different charges. So we now be equals, if I'm picking any point, it will be what? Inside the plate. So it will now be what? The amount of electric field divided by 2. So what is electric field formula from what you studied? Tell me. I told you the other time that whenever you want to write electric field formula, always write it in terms of what? Dielectric. So from what I've given to you, what's electric field in terms of dielectric? Don't waste my time. You forgot in it. It was what? Q over. You say Q. What is this one?
Charge density.
Charge density. Abi, what do you call charge density? Phi. Abi, don't forget all these Latin terms. It's important too. So now, that's what I'm saying. So you have I said always make it because you are talking about parallel plate capacitor. Is there no distance of separation? There is distance of separation. There is area of the plate. You understand? So that is why whenever you want to write electric field here, always make it. What is this one? Q over A. So it will be Q. Are you there? Over A absolute naught times. If you are talking about in terms of this word, guys, if you go by this is V over D. Are you there? Yeah. So if you go by this one, I said electric field is a vector quantity. It's V divided by D. And if E equals to Q over this one, whatever, what will now be the V, the potential along this one? It will now be equals to, you understand what I mean by that now? So always keep that in mind. So if I'm writing my electric field in this form, I also don't have issues with this as the formula of electric field in terms of what? Dielectric. So always have this because it's very, very important. Because that is what I will always use right from now to get my plan. So now, don't be afraid. It is all well. Don't be afraid. We are still moving. So what I'm trying to say here is now, if I substitute this one directly to this, what will I have, guys? I thought Q over 2A absolute naught. Are you okay with that? Are you okay with that? So, or any problem? You understand? What does A stand for? What does this one stand for? Dielectric. What does this one stand for? Charge. So don't just get it twisted. All these things are still what you know. So basically, I'm saying electric field between one plate of a capacitor. Electric field between one plate of a capacitor is E over 2 pi absolute naught. Is that not what I'm saying? Not what I'm trying to explain here. That is just that. It's always getting. But if I now want to calculate the potential difference between one plate, what will be the answer? Potential difference V is equals to what? Talk now. Electric field times what? The distance. That's where we are going. So potential difference between one plate of the capacitor will now be equals to one plate. That is Q over 2A absolute naught multiplied by D. This formula is also important to always keep in mind. That is PD between one plate of a capacitor. So students should always keep this in mind because we need you to solve direct questions as we move forward. So because you see question I ask you calculates the what? PD between one plate. So you want to know that the formula is having 2 under. Now we say where does 2 now come from? And that is why I'm trying to what I'm trying to analyze and for you guys to work. For you to get. So now, if we have this as V, then what will now be our force? Everybody knows that F equals to EQ. Do you remember this one on electrostatic? We've done this now. Yeah. F equals to EQ, equals to F over Q. Yeah. So if we have this electric field direct solution, we know is our Q over 2. You have a 2AE naught times another Q. What's Q times Q? That's Q squared over 2A absolute naught. Please always keep that in mind because this is the direct formula we use, and that is where I'm going. So please, that is just the first part of this word, introduction to capacitors and dielectrics. I hope you understand some, and I hope you have new formulas that you have to keep in mind that you've not met before. And that is one thing about physics. So the first part is this that we have done, understanding capacitors in terms of dielectric, explaining parallel plate capacitor, explaining the work done, energy and heat dissipation in capacitor, explaining different types of capacitors, spherical capacitors, cylindrical capacitor, spherical capacitor separated by a distance of L, the one separated in form of concentric, and so on and so forth. So we've done the first part. The next part of this topic is the one that is the most interesting part, which I believe we've learned in early classes, we call arrangement of capacitors. So this one we are going to do a lot of numericals here. These are series and parallel arrangement, which I believe you might have studied that in your early classes. So we move to the next part, and the next part I'm waiting for you guys to be through is arrangement of capacitors. Now, let me ask you guys a question. So far, so good. Before we move to the next part, what is the problem you have? I'm here. Your hand is up now. No. It's up. Oh. You must talk. Your hand is up. You must talk. What's the problem you're having? So far, so good. Any problem? Talk. You are free to talk. Any problem so far? So
The formulas are too much.
the formulas are too many. Okay, let me tell you the one you need to keep in your brain. Are you ready?
Yes.
Number one, parallel plate capacitor. You can see I did example there. E naught A over D. Take it. That one is simple to put in. Now, another one you need to keep in mind. Capacitance of a capacitor in terms of what? Electric field and dielectric is important. Like what I'm saying is you can see electric field in terms of dielectric. Electric field is what? Absolute naught over what? Over dielectric. This formula, that's what I'm saying. This one, it's very, very important. I'm giving you the most important formulas now you have to keep in mind. Like I said, in terms of types of capacitor, please, that one is simple to put in mind. What about if you are the one that is deriving it like me, like on physics on our most galaxy? What about if you are deriving it on your own? But you will not see that one is even the more true because I have to be integrating and doing a lot of things. You understand? But you just need to understand the formula alone. Now, we talk about circle. Whenever you have what? A circular what? Which is like a sphere. You know, we are always comparing this thing with sphere. When we started, we said the formula is what? Just don't stop your legs. Just 4 pi absolute naught R. 4 pi absolute naught R. And if somebody wants to start okay, I sabi now, if it is Q equals to CV, the formula is Q equals to CV. Let me make C sort of formula. C is will now be equals to Q over V. I know V from electrostatics. We've done that. Electrostatics and Gauss law. Abi? Now from that, we have V had to be equals to what? KQ over what? Over R. Substitute back there. You get, oh, you don't need all that. What do you need? C is equals to E naught A by D. Parallel plate capacitor. E electric field is equals to what? Charge density over absolute naught. Formula 2. Formula 3. We are talking about spherical capacitor. C equals to 4 pi absolute naught R. That's formula 3. I'm giving you important formula. The next formula, which I believe any classes, you know that one too. Everybody here should know W equals to QV. Yeah. And you should know energy is RCD squared. Yeah. What about that? What about its dissipation or dissipation? RCD squared too. All these ones are simple now. What about work done? CV squared. Don't make mistake between work done and its dissipation. Don't make mistake between work done and energy. Energy is RCD squared. Work done is CV squared. Or you have a question. This is why you are smiling. You are smiling. Only God knows why you are smiling. You want to ask a question. Energy is RCD squared. It's the same thing as dissipation of heat too. So nothing more. And if somebody asks, you know why I'm showing you all this one? This one has some questions can be in form of conservation of energy. I can tell you, okay, look at me now. It's not that I like giving you what it is. I'm moving with respect to your syllabus. I believe I can get a marker. Now, if we have this now, and we have a spring, and it's tied up a ceiling like this, and it was now connected to a parallel plate capacitor. Are you getting it now? Now, you are now asked the elongation of the spring. They ask for the elongation of the spring. How will you solve? You have to convert. You let them know that what the force in pulling this, everybody know force in string is F equals to KE, abi? It must be equals to the force of this one. What's this one? Q square over 2 AE naught. So you now calculate the value of the extension. You can see question like that. That is why we need to understand concept. You can see force in string was connected to a capacitor. What happened? The forces will be conserved. That is one form of force will be converted to another form of force. What is the force in a string? You guys know force in string is AE. It's always what? The force first. You guys don't know that. Talk now. Forces in string. When a string is stretched, natural length is X. So we say the direction of the force. When you stretch a string like this, a string is always like this. I will always explain everything. It's having initial length of L. There is another type of force inside every wire that you can watch that can regain back its position when it has been elongated. Everybody know when you stretch it, what happens? It comes back to us. So we say it has a restoring force. Are you getting it now? So there is a restoring force in strings. So this restoring force is always proportional to the length when you stretch it. So please help me change this. This restoring force is always proportional to what? To the length. So we now say the length is what? It's now denoted by extension, which in your textbook you see as E. So if force is now proportional to the extension, basic class. This is basic class. So F is proportional to extension. What do? When you want to change proportional sign to equals to sign, what happens? There will be a constant of proportionality. That's F equals to K. Famous formula. F equals to K. That's the formula you use for according to what's the name of that man said I did yesterday? Hooks. Hooks. Have you heard about Hooks law before? Yeah. Thank you very much. You are responding now. I love that. So please, that is all about that. So what I'm saying is, I look at this one. I don't connect spring with what? Parallel plate capacitor. What is going to happen? Are there no forces between plates of capacitor? Force stay here now. So forces are converted from one force to another as energy can be conserved in what? In everyday life. So I hope I'm communicating. So thank you guys. That's just that about that. So that's why I'm showing you all this. But the least about this is that next week class is going to be class with respect to calculations. That is when you know where you go. I will bring the calculation book here that we are going to solve. You know, it's very, very plenty. So you are going to solve. I will not give you. No, I told you after my first, this is my third week. I told you my 3 weeks are for classes, 1 week are for calculation. Trust me, I get them plenty. When it comes to calculation, but before I start solving questions, you need to know what. Now you now know that you know something. Read against next time because it's calculation class. Next week Saturday. So you understand. Read against that. It's very, very important. So we move to the next part. Arrangement of capacitors. Very important. Arrangement of capacitors. Arrangement of capacitors. So read your concept notes. Now, early classes. But I have my friend here that doesn't attend early classes. What are we going to do now? Because me, I will not explain too much here. Arrangement of capacitors. For those who doesn't attend early classes, what are we going to do to you now in this one? Because I already explained in terms of what early classes. We have capacitors are equal length, always have that advantage. So let's start before we do capacitive circuit. Let's take some important things. The second type of arrangement we call parallel. Just don't know. My spelling of parallel is always wrong. Parallel, single Arabic. Now, you have parallel arrangement. Everybody should know. Please draw. Don't waste time. Now, in early classes, we know capacitors can be arranged in series and parallel. Now, the arrangement of capacitors are just the reciprocal of your resistance. I hope students to remember that early classes. Now, for series arrangement, the total capacitance we call equivalent, C equivalent. Some people say C total. Please, you can listen. C equivalent for series arrangement of capacitor is C1, C2 over C1 plus C2. I hope students still remember these early classes. And if you have more than 2 capacitors that are arranged, you can say effective capacitor plus C equivalent is equals to, or we can say, excuse me, 1 over C equivalent is 1 over C1 plus 1 over C2 till infinity like that. It's continuous. When they are more than 2, you can use that as 1 over C equivalent is 1 over C1. But if there are 2, directly you can use C1, C2. You can use this one too for when they are 2. I'm just telling you this is directly, for example, we are going to take some examples on that. How to start about that. Then for for this type of arrangement, we say the equivalent capacitor, C equivalent or C total, is now equal to C1 plus C2 directly. And if they are more than that, you can say C equivalent is C1 plus C2 till what? Till infinity. This is the way we solve arrangements of capacitors in early classes, which I believe everybody here should be able to solve that without any mistake. It doesn't stop there, because when capacitors are arranged in series, we need to understand quantity of charge. The same quantity of charge is passed through them. So you can also write here that Q is same. And because Q is same, that means the potential difference are not the same thing. So if I connect this thing to a battery, maybe I show you at this side. First one, second one, I'm connecting to two ends to a battery. And when the switch is closed down, I'm going to have something like this. C1, C2 connected to a battery, like this, plus and minus. I hope students are following. Now, in this case, the same quantity, Q is constant. So far Q is constant, we say potential difference is not safe. So always keep that at the back of your mind. So what we do is that if you want to get the potential across the first capacitor, directly we use the divider rule. Early classes, you might have been told about that. And for my friend that doesn't attend early classes, yes? Yes, plus should be longer than minus. Thank you very much. That is that. Then we have, in this case, we have to get the V across this one is going to give you, Q equals to CV. That's the formula we use for capacitors. Are you there? Are you there? Don't be tired. If you are tired. So, because the arrangements are not the same, we say we have C1, C2 is equals to V2 over V1. This is the logic we use whenever we have series arrangement. Always keep that in mind. So it's very, very important to know that the first capacitance divided by the second capacitance is equal to the first voltage divided by the second voltage divided by the first voltage. All these are elementary stuff that I believe you might have learned. And if you are having issues with it, we are going to take examples of each of them. They are very, very simple. I will soon stop now. I'm having just 42 minutes more, so I have to up my game. Now, listen, guys. 42 minutes is too small for please, especially if you have a lot to talk about. So, but all the same, I will stop where the time stops. I have a time that is fancy, so I will stop when the time stops. Even if it is halfway, I will just stop like that. When you say now. Now, let's see. Now, for voltage across the second one, if you want to know C1 voltage will now be equals to the way your teacher will explain to you. I don't know if you still remember this one. I want to know the PD that flows through this, the PD that flows through this. The same potential difference is not flowing through there. You know very well that Q is equals to zero. So from this, the same Q is flowing through them, but different potential is flowing through them. So it's very simple to know. And if you don't want to use the formula, you can always use your own formula one by one. Calculate the total, all these ones are non-story. That is what your teacher will teach you during your UTMA classes and those days of your listening. Calculate the total C, calculate the total Q. We like that. Then when you now start looking for the one that you pass, divide that directly you have answer. You don't waste time in physics class. Directly you have answer. So I can say the first one will be C1V over C1 plus C2. The second one will be, what I'm saying is that voltage across the second one will be equal to C1V over C1 plus C2. And voltage across the first one will be C2V over C1 plus C2. You can tell me that about this because I am using my brain that they are connected. When they are connected in series, they have the voltage is always upside down. So I'm just using a kind of divider rule. What does this stand for here? The total V. Should I write it as VT? So that you understand better. V total. What am I saying, guys? Should I give you an illustration? Look at this. We have, let's take this one to be 10 microfarad. Let's take this one to be 15 microfarad. Are students here? Yeah. Are you here? Yes. Thank God you are here. Then I am connecting this to a 100-volt battery. Don't disturb yourself. All these things are doing. You don't say you want to be using one way, two way. Nobody have. I don't have that. Time is precious. The name of time is precious. Now, here, I will soon finish that. Now, I ask you, what is the potential difference that will flow through C1 and C2? As I have said, that C is not the same. It is only Q that is what? That is, you know, I can get the Q. Look at your traditional method. Traditional method. Look at traditional method. From traditional method, we can see Q equals to CV. Traditional method means old school method. The method your teacher will explain to you. Now we are in the 21st century. This is 2021. So we don't use traditional method again to solve questions. Now here, Q equals to CV is traditional method. Now everybody knows I have 10 and 15 are connected in what? Are connected in series. So effective capacitance, I mean, there are two. If they are one that you guys know this one, always use this one. Change your lifestyle. Change your style. Change your style. Another style. You understand? You need to change your style. Now, effective capacitance now, I can now say C equivalent. I'm just solving. Write a good note. Will be what? 10 times 15 over 10 plus 15. Traditional method. Please, this 15 cannot cancel this 50. Oh. I beg you. 150 divided by 15. What's the answer? 10. Divided by 25. What's the answer? 6, Abby. Talk now. 6 what? Microfarad. That's C equivalent. Now, I know the same Q will pass through there. So Q total. Q will now be equals to what's C equivalent? 6 times what's the 100? So that's what? 600 microcoulomb. Abi now? But if I want to do it in that mode, I'll change it one times 10 to the minus 6. I'm not doing that one now. I just want you to see this. Please listen, be attentive. Traditional method is too long. Now, I know that the same Q that pass through this one, we pass through this one. And now start again. See, traditional method. Q is equals to CV. God punish all these our teachers then. God punish them now. Because they intentionally want to give us problems. And when they know this thing, they will now want you to follow protocol. Professors, I'm sorry to use that anyway, but all things being equal, you just need to work. God will not punish them. God will be with them. I'm just joking. Now we have from here we have V is now equals to Q divided by C. That one is not a problem. It's not a problem. So now, what will I do? What's my Q now? 600 divided by. Talk now. What's that? 60. 60 microvolts. Now, 60 will flow through here. Everything is 100. That means 40 will flow through that one. But you can also do that one to say V is equals to Q by C. The same Q. What's that? 600 divided by, what's the C? 15. What's that? 40. Do you understand? Microvolts. So what I'm saying is that 60 will flow through this one. 40 will flow through this one. This is the traditional method that teacher taught. If not for them, we can't be here anyway. But one thing is that the professors are. You will understand what I'm saying. Professor can intentionally waste a whole year. Not that you are getting carried away when you are writing projects or you want to go and submit something. The professors are, I don't want to use that because I'm on camera. So let me just skip that. So now, the point about this is for you to know that this is too long. You can see what we've done. It's too long. I can quickly use the divider rule and get the answer. So far I know that what the C is the same thing. I don't need to waste time. Now, should we go by the look at this one? Look at this one now. Let's verify our answer. What's V2 now? C1. What's C1? Talk now. 10 times. What's V2 now? 100. This V2 now. Over C1 plus C2. 10 plus 15, Abi. What's 10 plus 15? 25, Abi. Here 1, here 4. 10 times 4. 40. What did you get? 40. So you can say you can now send something to your professor now. If it is prayer, of course, send something to them. So you can use any one you wish to use. These are elementary capacitors, which I believe you have learned in your early class. So it's always good to what to know this divider rule so that directly you can get answer without start distributing one form of what potential over the other. Am I communicating? So if this is rough, we can look for a picture perfect one, which we are going to draw examples for you to see clearly what we are talking about. I hope you guys are right. Any questions? Any question? Smile now, your faces are scary. You have to smile. Your faces are scary. She's the only one that is smiling. Everybody here is just, you want to eat me? Please, you smile, at least smile. Smile. Nobody smile at the back. I'm happy. Somebody can get me water. I need water. Now, please, I'm dehydrated because you are not smiling. I didn't know you are smiling. I will not be dehydrated. It's because you are not smiling. Suppose you smile. Just try like that. It's too fast. Some of you are tired. You are just using style to, you are just using style. So get me water, please. Bottle water. Do you have to? Thank you. That's big boy. Buy something for the teacher. So let's move on, guys. Now, should I make it more elaborated? Should I make it more elaborated with an example? Or you understand? No. I should elaborate. I should demystify. I should simplify. I cannot multiply like that. If I multiply your complexity, that means you are going from complex to complexity. And that is not good. Now, I should not be going. I can see. I can see that you are being affected with something. No, because this I'm not yet through. I'm only trying to explain a situation whereby you have capacitors that are arranged in series. One thing you have to keep in mind, please be attentive, is that whenever capacitors are arranged in series, there is one thing that is the same. What's that? Quantity of charge. We have discussed from the first part of the topic that Q is equals to CV is the formula we use for all types of capacitors. And most likely, capacitor you see around everywhere you go is for parallel plate or capacitors. Now, the formula is what you are going to use also in arrangement of capacitors. Early classes, you have learned that capacitors can be arranged in series and in parallel. You have a question? This is just series, not series. Along the straight line, directly connected to the potential, that is series. Parallel is when it is not directly connected to the potential. See this. This is the potential. The potential here is coming, reaches the junction here. When we talk about nodal analysis, then it's split. That's parallel. You understand? You understand better. We are still going to go for electricity. Under that, you understand all this Kirchhoff current law, Kirchhoff voltage law. We'll talk about all this. You are going to get all this. Here we are only going to analyze, please be attentive to the analysis. So what I'm saying is that whenever you have series arrangement of capacitors, the same quantity of charge is passed through them. That's what I'm saying. So traditional method that our instructors might have given to us is that Q is equals to CV is used, and we can use that one to start breaking that. We have talked about, look at this, as it starts flowing, what happens? Positive charge, negative charge. You understand? Positive charge, negative charge. It continues like that. The flow is like that. You know, I said with time, some electron will escape, and that's where you have dissipation of heat. We discussed about this. So please always have that at the back of your mind. It is not what you can't understand, but by constant practice, it sticks. It sticks. You don't need to carry anything. You know, I do say that. You don't need to carry anything. Just do it directly and you have it. This is what I'm saying. I will help you rewrite them for understanding sake. Just what? I just classified things. I gave a question, like a simple, these are elementary stuff. You guys are A-level students. What is it? I used 100, I mean. Is it 100 volts? Yes. I classified two capacitors that are connected in series. And if I ask you that, what is the, you can say question, number one, all these elementary questions. Find the what? Quantity of charge that pass through the whole system. What's the formula? Q equals to CV. Number two, calculate the voltage that enters what? C1. And the voltage that, but because we said that the same voltage cannot pass through there. Whenever capacitors are connected in series, voltage are not the same. It is only when they are in parallel that voltage are the same. The only thing that is the same here is what? The Q. So if you know from, if somebody asks you to calculate the quantity of that, just say Q is equal to CV. Now, how many C am I having? I'm having 2 C's. I have to get the equivalent of the C. That is the total capacitance. And we have discussed. We said equivalent capacitance of series arrangement when they are 2 is product of the 2 divided by the sum of the 2. This is what I have done. This is the method we use to calculate equivalent capacitors. I know by now you are getting it now. Can I move on? What is 10 times 15? Please communicate. 150. 150. 10 plus 15. 25. This divided by this is giving you 6 micro. What is the sign of capacitance? That is farad, Abi. You understand? I'm still working in terms of micro farad. Read it like that. The next question I ask me, find the potential difference in C1. Because this 200 volts is passing through the 2. But different what? Potentials are passing through each of them. So what do? I will still use the same formula that we have learned from our teachers, God bless them, Q equals to CV, to get that. How will I get potential? Make V to a formula. Oh yeah, communicate. I love an interactive class. V equals to Q over, please talk very well, Q equals to what? Q over C. Now let's start. The same Q is passing through them because they are in series. So what happened, guys? What is Q? We did Q now. Okay. We've not calculated Q, have we? Let me calculate the total Q first. Q total. Sorry about that. What is C? C total. 6. What is V total? But one thing is, let me just make this one 100 microvolts. So that, because I'm not converting, I have reasons. If you're actually following me, if this one is in volt and this one is micro, I have to over times 10 to the power. I don't want to use 10 to the power minus 6 or anything now. Leave that one out. So 6 times, what is V now? 100, have you? So what's that? That's 600 micro. What's the sign of quantity of that? Coulombs. I hope you still understand that. What happened to her? You want water? Don't worry, let me take my one, I'll give you the rest. Now the next one, I know it's you that you want water. You are the one that want water. I can easily read through you. Oh yeah, now both of you need water. Now, the next thing I will do here, guys, is now I haven't done this. I will also okay, fine. This is the total quantity of charge that passed through your whole setup. I now need the potential difference. I will now start again. Q is equals to CV. Well, you said something like that. Make this your formula. V is equals to Q over what? Over C. I'm taking it calm, slow, and simple. So you'll say Q is the same thing everything, 600 divided by, what's the C in the first one? By 10. That's the first one. Or 600 divided by 10, 60 volts or 60 microvolts. Anyhow. So that's the answer. Another way, look at formula that is very fast. When you know one is 60 volts, everything are 100. What will be the one in the second one? 40. So those are things you see people doing. But you want to prove it, the same formula again. V2 is equals to Q over C2. Have it? Maybe C1. So you say Q is uniform 600, or C2 15. What's the answer? 40 microvolts. So that's that. And that is traditional method. But I said nowadays we don't use traditional method, we use divider rule. So for C1 over C2 is V2 over C. So directly you can calculate the answer. So do you want to listen to the new method? I mean, you are okay with it. You are okay with it. But me, I don't use this one. When I start doing my own, you see me print, I'm done. Bam, 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 bam. I'm okay. So let me take water. How many minutes more to that? That one is 1 hour. 1 minute. It's too late. You want to go and go and sleep in the hostel. Or you are going to like, what's her name? What's her name? Sharon. Sharon, you are going to
Fisher.
Sharon Stone. You know Sharon Stone, popular artist. Now we move. Now you understand the second law now. Look at the second formula, the one I was talking about. I want to get the V in the second one. It will be, listen, Q times V1 or V total. I said Q C1 times V total over C1 plus C2. If I want to get the V in the first one, I will say is C2 times V total over C1 plus C2. This is fast because I don't need to go through the process. In fact, it's because I'm writing the formula out. It's fast. What is C1? Please stop. 10. What is V total? 100. 10 times 100 over 10 plus 15, 25. Year 1, year 4. 10 times 4, 40. Is that not the same thing? 40. This one, let's do it together, guys. I'm with you. 50 times 100 over 15 plus 10. That's what? 25 now. Year 1, year 4. 15 times 4. 6. So anyone you are using, guys, you are free to use anyone, but it is better to use the what? They said some people do say the old way is better. The old way is safer than the what? The new way. Old way is better than the new method. I'm talking about probable that you have to go back to the things of the old. But for me, I don't actually believe in that. It is not in every situation. Nowadays, new method is faster than it's even when we are differentiating and integrating, you will see. When we are integrating in engineering, you see a lot of new methods now. Now you don't need to be using one changement and all these things that professor will be wasting our time in schools. We don't need all those ones. Why do we need all those wasting of time and stuff like that? We don't need it. Use DI method. You differentiate, integrate, cross multiply, answer. Yeah, you are good. All you are using Leibniz integration. Who cares? I don't use all those ones. So that's not the matter, but you get to know it when you get there. With time. Engineering is the sweetest. For those going for engineering, physics is so simple to be honest. It's very simple. You are going to love physics. But if you are what? If you want to go and study engineering, physics will be your favorite and mathematics. You want to do chemistry, you want to do chemistry. It only takes people that have a penchant in chemistry that can teach chemistry. No one like me, I love chemistry, but in fact I love chemistry and all these stuff. But I know all this one very well. You understand? But I love chemistry from. So let's move on. Can we move on? Now, look at this is not part of it where something I'm just showing stops. So I will clean it. You already have it on the first. Please shut up and listen. Now, in this case of parallel arrangement, please you can write that voltage is same. Voltage is same. So voltage transfer. So if somebody asks for Q, you can say Q equals to C1 V. This is the same thing. Then Q in the second one equals to C2 V, because voltage is always same in parallel arrangement. Voltage is the same. It doesn't change. Here, quantity of charge is same. Here, what? Voltage is same. So it's simple to just use direct formula and get the answer. That's not all. Now, listen. Another shortcut formula, bless you. Another shortcut formula I can give to you very quickly is when you have the same number of circuits of capacitors that are arranged, I still find it difficult. As I still find it difficult, I don't understand why students still make mistakes in this. When somebody gives me, look at this one, a kind of arrangement. Watch, guys. I have this, then I have 2 microfarad, 2 microfarad, 2 microfarad, 2 microfarad, 2 microfarad, like that. Then someone now asks me, I should calculate, please listen and look at the word. I should calculate the what? Effective capacitance. You now start, okay, 1 over C, 1 over C1, that's the formula, plus 1 over C2. You don't need this. You don't need all those things. Whenever you have equal capacitance arranged in series, effective capacitance, C equivalent, is equals to C by N. Direct shortcut formula. You can always use it. You will not see it in your textbook, but it is good. The answer to this one will now be, what is C? What's C? 2, Abi. What's the capacitance? Value 2. How many are there? I believe 1, 2, 3, 4, 5. 2/5 microfarad will be the answer to the question. Look at your traditional method. Let's use the traditional method. Are you there? So it should be 1 over, help me out now, 1 over C equivalent equals to 1 over, what's the first one? Please help me out. 2, 2, 2, 2, 1, 2, 3, 4, 2. I hope you should understand this. Everybody know this one will give you 1, 1, 1, 1, 1, 1, 1, 1, 5. Abi? 1 over. Any problem with this one? This is elementary mass. Abi 2 into 1, 1 plus 1 plus 1 plus 1 plus 1, 5. What happened? Cross multiply. C equivalent to 1, 2/5. Not the same answer. This is not the same answer. So when you have n capacitance and they are arranged in series, effective or equivalent capacitance is C/N. Simple. Very, very simple. Life is so simple if you know what you are doing. So that's just that. So keep that one in mind. You can see, I told you, this is basic. No, this is, we are getting here small, small. Because I'm now taking it to another level now. So the last one we are going to talk about, well, I have 10 minutes more. How many minutes more, please? Because I'm working with time. I want to see 20. Less than 20. Okay. Now, the next one, now, if it is in terms of voltage too, in terms of voltage, if they are connected in the other way, it's the same thing. It will be V over N. You can also do that. If you calculate the voltage in each of them, and they are connected, so you can also write, you can say V equivalent voltage if you want to calculate it what. But don't worry, just like this one. You're going to get there. So please have that at the back of your mind. So please, all these are what I believe you might have studied in early classes. And if you have not studied all this one in your early classes, I am helping you. That's why I'm taking my time to make sure understanding is what is important. The way people are looking, I'm beginning to spot. To think I have to stop this class, but I will still finish because I still have what I call the last part I want to talk about today. I call capacitive circuit. So you can write capacitive circuit. Capacitive circuit. That's the last one. Don't worry. Capacitive circuit. Capacitive circuit. Capacitive circuit. Now, what do you call a capacitive circuit? Now, like I said, guys, arrangement of capacitors are just in two forms: series and parallel. Are you guys there? You are not there. What will I do now? I want you to be here. Of course, what happened? You are saying like this. 17 minutes more. Capacitive circuit. I must finish you. Please, I'm rubbing up. I'm rubbing up. I'm rubbing up. 17 minutes more. So please, let's be attentive. The something will stop automatically by 17 minutes, and I'm stopping. Immediately it stops. They are stopped.
No.
Let's go to the hostel now. We'll continue the hostel. I will come one by one to your hostels. You have four hostels. I'll come one by one to your hostels. And I will just take you in groups. Now, let's take it now. Capacitive circuit. Now, when we talk about capacitive circuit, so you can just say, this is the simplest form. Nothing to write now. Yeah, right. This is the simplest form of a series and parallel arrangement. The simplest form of series and parallel arrangement. So what we are saying is that it is possible for us to connect both series and parallel together. Then when we have that together, we call it a capacitive circuit. Now, let's take the simplest one for understanding, like we have 18 minutes more or less than that. We have this connected to this connected to this, connected to this, connected to this. Okay, series. We have this. Oh my God. Please, no noise. I don't want noise. You know me very well. No noise, please. You know, not be small people. When my capacitor has even taken up my spaces, what will I do? So let me say 9 microfarad, 3 microfarad, 6 microfarad. Then we have 20 volts. 20 volts. So we want to take the simplest form of a capacitive circuit in this class. In the next class, all things being equal, we are going to continue with the class. Now, as you can see, this is a combination of what? A series and parallel arrangement of what? Of a capacitor. And this we call a simple capacitive circuit. Now, different questions can be asked about this. It's the same thing as writing it anywhere. I just want it to be here. Now, different questions can be asked about this as to calculate the amount of what? Quantity of charge that flows through something, the amount of potential that flows through each of them, and so on and so forth. So that is what we want to quickly distribute. Early classes you might have discussed about how to calculate all these things using your keyboard to see it. But the first most important thing is to calculate the equivalent capacitor. Equivalent or what we call C equivalent. As we have studied now, we now being forced. What is the parallel arrangement? I'm going to say what? 3 plus 6. I mean, what's 3 plus 6? I will first of all resolve this. Early classes you study this. Parallel is just 3 plus 6. What is 3 plus 6? We just studied that. Whenever they are in parallel, you just add what? You add them together. 3 plus 6 is what? 9. So I have 9 and 9 now connected in what? In series. So how would I resolve through series? I have, you can see, it is just N and C over N. I don't want to waste that. Look at what I'm talking about. I just say 9 divided by 2. What's 9 divided by 2? 4.5 microfarad. So that is the equivalent capacitor. Ask your question. Look at your long method. I don't want to be using long method. You have to get along, flow with me, so that you can score A in your due bed. You have to flow with my method. It will help you. I've not started work example. I do tell you that. All these ones are concept related class. My work example class is purely calculations and questions from due bed. And we are going to take that. But by that time, you need to know something. It is what you have eaten that you are going to use to fly. What a bird eats is what the bird uses to fly. That's what the Bible will say. Now, we move. How do I come about 4.5? Traditional method. You know it now. 3 plus 6, 9. 3 plus 6, 9. 9 and 9 are 9 in parallel. So when you say 9 times 9 over 9 plus 9, same story. 81 divided by 18, 4.5. Yes. I mean, from what I've given to you, fine. But now I see long. 9 and 9 are what? Are N capacitance. And then from N capacitor, what did I give you the formula? It will be what? C divided by N. What is the C? 9 and 9. Because this and this is giving us 9. No be so. That's so. So 9 divided by 2, anyone you wish to use. Another person will not even use this one. We just start 1 over C, 1 over 9, which is this one, plus the answer of this one, 1 over 9. Same answer. Do you understand? SCF 9, 1 plus 1, 2, 2 over 9. Then you flip it over, chica. Are you getting it? Very good. So 9 divided by 2, then you have 4.5. Any of the method is acceptable. You know as much you are getting. So what I'm saying, guys, is that the equivalent capacitance that is flowing through this rubbish is what? 4.5. So if I want to get the quantity of charge, what will be that? Q equals to, talk now, CV. It's not C over V, CV. Now, we've talked about that. This is where the total quantity of charge that will pass through this one, Q is equal to, what's the total? That's 4.5 times, what's the total voltage? Please stop now. 20 times 4.5 is what? Somebody like calculator. 100. And what's 20 times 4.5? 20 times 4, 80, 90. 60 and 90. 20 times 4, 90 now. Let me hit you. 20 times 4, 80. Half times 20, 10. 80 plus 10. 90. Are you there? So if 90 microcoulombs, I'm just taking that, is now being passed here. I have told you that what charges will move this, who is that one? This charges will move from negative, having to positive. So what's the answer we have here? 90. So here we have plus 90. Talk now. Here we have what? Minus what? 90. I'm just talking about the distribution of the flow of charge. You listen because it's almost time up. Less than 10 minutes more. Sorry, I know you guys are tired, but you have to get used to your 2.5 hours class sometime. Now, from here, we take it from here. Now, that means 90 has entered here. 90, the amount of charge that has entered this one is 90. But we said something when we have this that is connected. You remember? When we have this that is connected, two things are involved. The same potential difference, we enter them. Is that also? The same potential difference will enter them, but not the same quantity of what? The same quantity of what? Charge. Now, what do? It's so simple. We can still move on by saying, okay, fine. We have gotten the total quantity of charge. We have gotten the total what? The total, what is it called? The total capacitance. So the total, we also know it to be 10, to be 20. So what we do here is that at this point, see traditional method, at this point, you now say, okay, therefore, again, the formula, you can see the formula of Q equals to CV. What is Q at this point? 90, Abi? Is equals to C. What's C at this point? Sorry about that. What's C? 9 times what? What's V? We don't know now. I'm talking about this particular point. I'm trying to analyze each section for you to see. Q at this point is the Q that is flowing. I think we calculated. 90 entered this place. What's the charge here? What's the capacitor here? Capacitor there is a capacitance there as well. 9. So I'm looking at the voltage there. V will equals to what? 90 divided by 9. What's 90 divided by 9? 10. So 10 volts. So 10 volts will enter this place. Now guys, if 10 volts has entered this place now, the 10 volts will now be distributed between this and this. You understand what I'm saying? So what I'm trying to say here is that if you say 10 volts has entered that place, that means the remaining voltage, the total voltage at this point is what? Is 20. So that means 10 volts will also be at this one and this one. But it is also possible for me, it is because I'm using 20. That's why I'm so lucky. What about if this one is not this? If this one is 24? You understand? It will just change everything or whatever. It is not necessary that this equal amount of voltage that has entered this place will enter these two places. So what I'm trying to say now is that your Q equals to CV is so important when you are distributing capacitive circuit and you understand the flow of the capacitance and the quantity of charge as well. So please always keep that at the back of your mind because it's so important. So now, because you guys are not O-level students, you are advanced level students, you are expected to understand that there is a proper method that we use to analyze capacitive circuits we call nodal analysis. So I will quickly do that in 6 minutes and I will call it today. Now 6 minutes, just 6 minutes please. Now we'll continue from there in the next class, trust me. Nodal analysis we are going to talk about it under current electricity. Now nodal analysis, very important. Now from nodal analysis, I will just give you an introduction to nodal analysis. A very quick one. So students listen. Now we have two charges. This is the question initially. I am rubbing up all these things now. I'm going to wipe them out. So if you are writing, you do that in what 30 seconds. Now from nodal analysis explanation, everything here is simple and clear. So you don't need to write all these diagrams. Now by equation of nodal analysis, you can just look at this. From nodal analysis of circuits, it's simple. Now, when we have 3 capacitors, it is very simple for us to calculate. You can have more than 3, you can have 7, you can have 17. Nodal analysis will work. But because your own A level is still elementary A level, if it is those one we take for what we call it now not Japan, but what's this name Cambridge. The Cambridge A level I do take those times. I take them something that is very tough. Your own A level is the A level. I don't see this one as A level. It's just a step ahead of, one step ahead of O level. That's what you are doing. You want to write quick pages, you know that we are talking about something. I do take you to Ibadan International those times. You understand? So you will see correct questions. Now moving back to nodal analysis. Now, for node analysis, we are going to analyze the potential difference. Now, listen, let's listen now. Listen to this. Watch. We have plus and we have minus. I said potential are moving from negative to positive. So we take the end of the positive to be what? The potential difference that we have, 20. The one that is negative, we take it to this end, we say it is what? 0. That's what we do. So we distribute the potential in two parts. That's the first step. Listen to this. It's a simple technique. Now, we now say, okay, at this point is 20, at this point is 0. We now take the interval between the series and parallel combination. I'm taking this interval now. I will take it as x because I don't know the potential that will flow through this point. I will take that again. I have a junction. I have two junctions, positive and what? Negative. The positive will take the potential, the negative will take what? The 0. It is just like that. That's the format. We want change here. You get that? That is the way it's being done. Now here, current is going like this. So I will now say at the interval between the series and parallel, that is when there will be a change of phase. You understand that now? I take the amount of potential to be here to be what? To be x. Now from my formula, please watch. You know the formula. Q is equals to what? CV. So that is what we want to use to formulate the equation. Let's start. At this point, you have Q is equals to Q now equals to C. What's the C at this point, guys? What's the C here? 9. I'm using this equation. C is 9. Open bracket. Now, what is flowing from here? We have the current is flowing like this. So what is the amount of our potential difference here? X. What's the one here? 20. So what will be there? To be X minus 20. Then plus, I'm using Q equals to CV to set another equation. Watch. Plus, we move. I just want you to see all this. All. Let me just explain it so that you guys can see it clearly. No time. I'm rushing to continue next class. From Q equals to CV, I'm forming another analysis equation. So I am at this point, I'm using Q is equals to CV. Watch. C at the first junction here is 9. X is the V here. At this one, 20. So what we flow through is X minus 20. I'm going to add it to the second one. What is the C here? 3. Please stop now. 3. What's here? That is X minus 0. What's X minus 0? Stop now. X minus 0 is what? X. Abi? Plus, what's this one, guys? CV again. That's 6. Are you there? Open bracket. What's this? Going like that. X minus 0. What's X minus 0? X must be equals to 0. So what we have is 9 open bracket X minus 20 plus 3x plus 6x equals to 0. Let's do mathematics. From here, 9 times x, 9x minus 180. Am I right? Plus another 9x is equals to 0. 9 plus 9 are 18x is equals to 108. S equals to 180 divided by 18. X answer is 10 volts. This is the voltage that will pass through this point. So from now, I can now get the voltage at each of the point by using my x minus 20. You understand what I mean by that, and I'm getting the answer. So please, what we have done here is called equation of load analysis. We used to compare different circuits rather than using the complex formula of Q equals to CV. Just take one point. If you take one point, now that you know that 10 is now passing through this point, it's now easy for you to get every other value. You understand? So that is your answer. Instead, you can see when we solved the other time, our answer to was 10. Do you remember the answer was 10 when we solved? Yeah, you can see that it's actually having the same value. So that is the best method you use on an A-level student, but you may have to use load analysis to form the position of capacitive circuit. So guys, see you guys soon. Thank you very much. Bye for now. Help me out.